Good morning, ladies and gentlemen. My name is Richard Henry. I'm the Deputy Vice-Chancellor Academic at the University of New South Wales, and I'd like you all to feel very welcome to this campus and to the CINTIA Theatre. This is a very special occasion, and I'm going to provide you some background, firstly about the medal and to a lesser extent about the person. So today we're going to present the Silver Dirac Medal, and the Silver Dirac Medal for the advancement of theoretical physics is awarded by the University of New South Wales on the occasion of this, the public Dirac Lecture. The lecture and the medal commemorate the visit to the University of New South Wales in 1975 of Professor P. Dirac, who was one of the greatest theoretical physicists of the 20th century. Professor Dirac gave 5 lectures at the university, which were subsequently published as a book, and the royalties of this book were donated to the university by Professor Dirac, which led to the establishment of the Dirac Lecture series. And the first of those lectures was given in 1979, and they've been conducted on a regular basis. And of course, today we have the 2011 lecture, which is to be delivered by Robert Lord May of Oxford. I'm just going to tell you a few words about him because a subsequent speaker is going to elaborate on things, but he holds a professorship jointly at Oxford University and Imperial College London, is a Fellow of Merton College in Oxford, and until recently was the President of the Royal Society and was the Chief Scientific Advisor to the UK Government and the Head of the UK Office of Science and Technology. Now, by the time you get to there in the CV, you know you're dealing with a very substantial person, and it rather reminds me of the person who was the designer of the Golden Gate Bridge. His CV said designer of the Golden Gate Bridge because he figured that after that there wasn't anything else worth saying, because if you didn't want to employ him on the basis of that aspect of his CV, there was probably no other aspect of his CV that was relevant. But frivolity aside, this is a very special occasion. We have a very special person here, and in order to celebrate that occasion, we're actually going to have a formal medal-giving ceremony and the obligatory photographs. So I would like to invite Lord Robert May to the stand so that I can present to him the Dirac Medal, and of course your role as an audience is to applaud wildly. Lord May. Now, I'm now going to dismiss him from the stage, and in fact I will leave the stage as well, but not before introducing Mr. John Hardy, who's the President of the Royal Society of New South Wales, who will provide a more detailed biography around Lord Robert May and also tell us a few words about the Royal Society.
Thank you very much, Professor Henry. I'm delighted to be here this morning at this very important event on behalf of the Royal Society of New South Wales, and I'd like to thank the University of New South Wales for inviting me here this morning. As President of the Royal Society of New South Wales, it gives me great pleasure to have just witnessed the awarding of the Dirac Medal to Lord May of Oxford. Robert Macready May's extraordinary gifts were very apparent when, at the age of 33, he was appointed Professor of Theoretical Physics at the University of Sydney. But the most extraordinary thing is that not so very long after that, he became Professor of Zoology at Princeton University, and then on to Oxford and Imperial College London, where he also now holds a chair in zoology. This, to me, is an extraordinary leap across disciplines, and one which our society certainly applauds. Throughout his life, Lord May has explored many fields, including biology, economics, infectious diseases, and latterly the global financial crisis. This diversity, this exploration across disciplines, constitutes the building blocks of today's Royal Society of New South Wales. Perhaps today's lecture, which follows, might give us some insights into this very important and increasingly relevant philosophy in today's world of democratised, freely available knowledge, in inverted commas. As many of you may know, the Royal Society of New South Wales is arguably Australia's oldest scientific learned society, tracing its antecedents back to 1821, when the Philosophical Society of Australasia was formed with the then Governor Sir Thomas Brisbane as president. The society re-energised itself in the 1850s and has existed continuously ever since. Such luminaries as Charles Darwin, Sir Douglas Mawson, Sir Edgeworth David and Lord May of Oxford have been members. As the Society's Act of Incorporation of 1881 states, the Society was formed for the encouragement of studies and investigations in science, art, literature and philosophy. We're following this all-embracing purpose to this day, and today's event and the subject of the lecture is certainly testament to this. Lord May was President of the Royal Society of London, as you've heard, from 2000 to 2005, and before that, Chief Scientific Advisor to the UK Government and Head of the UK Office of Science and Technology. He was awarded a knighthood in 1996 and appointed a Companion of the Order of Australia in 1998, both for services to science. In 2001, he was one of the first 15 life peers created by the House of Lords Appointments Commission. In 2002, the Queen appointed him to the Order of Merit, the fifth Australian in its 100-year history. His many honours include the Royal Swedish Academy's Crafoord Prize, the Swiss-Italian Balzan Prize, and the Japanese Blue Planet Prize. He's a foreign member of the US National Academy of Sciences, an overseas fellow of the Australian Academy of Sciences, and an honorary fellow of the Royal Academy of Engineering and several other academies and learned societies in the UK, USA and Australia. In 2007, he received the Royal Society of London's Copley Medal, its oldest, dating back to 1731, and most prestigious award, given annually for outstanding achievements in research in any branch of science. It's evident that Lord May's fundamental views about knowledge and philosophy can be traced back to the work of Paul Dirac, and it's actually worth making some comparisons. In 1932, at the age of only 30, Dirac himself was appointed the Lucasian Professor of Mathematics at Cambridge. In fact, he was elected a Fellow of the Royal Society of London in 1930 at the age of 28. And like our distinguished medalist today, was awarded the Society's Copley Medal as well. Both gentlemen were extraordinary achievers at an early age. The importance of Dirac's work to us in the Royal Society of New South Wales is that not only was it extraordinarily groundbreaking at the time, but his famous wave equation, which introduced special relativity into Schrödinger's equation, reconciled relativity theory and quantum theory mathematically. The idea of eliminating borders between disciplines and hence of not setting up silos of knowledge is fundamental to the precepts of the Society. And I suspect that today's lecture will support that philosophy. It's worth noting that one of the current Vice Presidents of the Royal Society of New South Wales, Emeritus Professor Heinrich Hohrer, who's with us today, became the Foundation Professor in Theoretical Physics at this university in 1975 and was able to attract Paul Dirac, one of the greatest leaders in this field, to come here. And as you've heard, the sale of approximately 6,000 copies of the book containing the lectures given by Dirac was able to, in fact, form the basis for the award of the Dirac Medal and the Dirac Lectures. So in closing, I'd just like to mention that with great pride, the Governor of New South Wales, Her Excellency Professor Marie Bashir, who's a patron of the Royal Society of New South Wales, will be investing Lord May with the award of Fellow of the Royal Society of New South Wales at Government House later today, and I'd like to take this opportunity to congratulate him in this auditorium for that now.
Thank you very much, John. I'd now like to invite Dr. Fred Osman, who's from the New South Wales branch of the Australian Institute of Physics, also to offer some words of congratulations and then to introduce the lecture.
Deputy Vice-Chancellor, Professor Henry, distinguished congregation, guests, fellows, this is to express my warmest congratulations to Lord Robert May of Oxford, to this prestigious award of the Dirac Medal in the name of the Australian Institute of Physics of the New South Wales branch. We at the Institute of Physics have been involved from the beginning in the 1979 at the Dirac Lecture presented by the Swedish Nobel laureate Hans Alfvén, with supporting the award at this initial and following occasion. We also thank the University of New South Wales for carrying forward these celebrations in cooperation with our community of physicists. The members of the Institute of Physics are honoured to celebrate the events, and especially this time for you as a colleague who entirely from our area. Dear Lord May, we are proud of you as the most eminent example for us all in our world of physics, with your unique success to the broader world of knowledge in science, applications, and the development up to key questions of politics and life. Please let me tell you from the Australian Institute of Physics that we are most grateful to you to have this very unique opportunity to hear you now on this wonderful topic of beauty and truth, the intersection in mathematics and science. Ladies and gentlemen, please welcome Lord May.
Well, first I should explain that my many virtues don't include the ability to give a lecture wearing a jacket. This is a slightly curious lecture, and it's a variant on one that was part of a series that Cambridge has annually around a theme, and the theme was beauty, and they thought they would lead off with one on beauty and mathematics, and they got something similar to this lecture instead. It's not quite the same thing, because the way I'm going to organise this is I'm going to begin by with the observation that if you go back into the mists of prehistory, where we just read the enigmatic signs in cave paintings and stone circles, it nonetheless seems fairly clear that people were, on the one hand, trying to make sense of the world around them, and on the other hand, it was intimately engaged with things that today we would think of more as the humanities. And indeed, the early Greeks were beginning to lay the foundations of mathematics perhaps more than natural science, were constrained in what they did by the notion that the perfection of the circle. I mean, one of the legacies of this is commonly misunderstood, that Ptolemy did a lot of silly stuff with epicycles, and then along came Copernicus, and Copernicus said the Earth goes round the sun. That is all a lot of nonsense. For first, the question, which is often on SAT tests, does the Earth go round the sun round the Earth, is they're in relative motion. That question doesn't have meaning. What Ptolemy did was take Earth at the centre, admittedly, and then a circle, and then epicycles, all circles, which in fact were correct to second order in approximation as a description of an ellipse with relatively small eccentricity, which is what the orbit really is of their relative motion. And Copernicus did something that was different and rather more elegant by taking the circle but moving, and he put the sun at the middle, admittedly, but it wouldn't have mattered if he put the Earth at the middle, and then he moved the sun sideways, off-centre, which would have brought horror to the Greeks, who felt everything had to be all circles, and his approximation also was exactly to second order correct as a description of an ellipse. So it was precisely equivalent to Ptolemy, but with a different aesthetic foundation. And that, in some sense, is the way I'm going to conduct the rest of this discourse, of saying first a little bit about the pure beauty, the somewhat icy beauty, the perhaps to many people off-puttingly abstract beauty of mathematics, and then turn to the more interesting question of to what extent are concepts of elegance, and for more broadly beauty, are they still of use in our attempts to understand the world? And then I'm going to end with some random thoughts. In mathematics, it's really quite different from the natural sciences, in that in mathematics you're dealing with pure logical systems. And if you say two sides of an equilateral triangle are equal, then the angles will be equal. And there's no ifs or buts about it, that's just a fact. The difference between that and the natural sciences is that in the sciences, however beautiful the theory, it's trumped by an ugly fact. I mean, many theoreticians would quite sensibly say you don't want to abandon the beautiful theory too soon because maybe the ugly fact is wrong, but as a broad principle, it's the right principle. And I remember my first encounter with this, like many school children of my era, and I'm unfamiliar with it these days, so I'm not sure that it still is, was Euclid's theorems in geometry. And one of the first theorems in Euclid's geometry is just that. Equilateral triangle, AB equals AC, angle B equals angle C. And how did Euclid prove it? The standard proof, you drop a perpendicular and you now say AB equals AC. The two triangles have the side AD is common, and it's a right angle, so that angle's there, therefore they're congruent, therefore angle B equals angle C. And I remember as a 12-year-old encountering this and arguing with the math teacher that it's blindingly obvious by symmetry that if the two sides are equal, the two angles are equal, and he told me in no uncertain terms that was not a proof. About 10 years later, one of the first things done by an interesting group of people when computers first appeared on the scene, and there began the thought of to what extent can we make an intelligent computer, artificial intelligence. And somebody had the bright idea of trying to implement a set of logical rules and then see if the computer could be creative. And they thought a good first test will be, is it going to be smart enough to work out you've got to drop that perpendicular to prove one of Euclid's first theorems? And what happened is the computer, doing something that no one in 2,000 years since Euclid had done, said the triangle ABC and the triangle ACB are congruent. AB equals AC, and then AC equals AB, and BC is common, so the triangle ABC and ACB are congruent, angle B equals angle C. It is a formalisation, I hasten to add, of the argument from symmetry. So, and it also says that in some sense this computer was smarter than Euclid. But of course, things became much more complicated as the centuries went by. We tend often to forget that the Greeks didn't really seem to have a clear idea of the number zero's place in the world, and that is arguably a contribution we owe to the Arab world, who certainly to them do we owe the tidy numerical thing, the system rather than I, and so on. And eventually the invention of negative numbers, and coming forward and introducing it for a reason rather than just for elegance, for the future discourse. For those not familiar with it, let me introduce you to the concept of imaginary numbers. Take the simple bit of algebra, x squared plus 2x plus 2 is 0. What's the value of x? Well, you can rewrite that as x plus 1 squared plus 1 equals 0, or x plus 1 squared equals minus 1. So x equals minus 1 plus or minus the square root of minus 1. The square root of minus 1? A number that multiplied by itself is minus 1? There is no such number. Well, let's set that aside and define it. Let's call I the imaginary number, and now we can go into an extended universe in which these things are that we now have a solution to that quadratic equation. And we have a concept that's extended the notion of real numbers to complex numbers, where the x-axis is the real bit and the y-axis is the imaginary bit. And we can play games with this. The next slide is one of the most magical equations in mathematics that some in the audience are familiar with and others not. And it's an equation that says the following. You can prove it by fiddling around in the complex plane. I'm not going to prove it, I'm just going to show it as an example of the beauty in its cold and icy form that you find in mathematics. And it's the amazing equation, simple as anything, and it says E, the exponential number, the number that enters when you say, what is the character of a function such that as you change the value of x in the function, the rate at which the function's value changes is simply equal to x? And the answer to that is the exponential function. Some number, some fundamental number, around 2.7 odd, called E, fundamental character of nature, if you like, E, raised to the power x is the exponential function. Pi, of course, is the ratio of the circumference of a circle to its diameter, another fundamental number, about 3 1/7. And this equation says E to the power I pi, so one fundamental number raised to the power imaginary number times pi, the ratio of circumference there, is -1. And if you're in the right frame of mind, that is really magical. And sidelight on pi, interestingly, if you don't understand this, and you don't understand the fundamental nature of these numbers, the Wisconsin legislature, about 100 years ago, moved and passed a bill to redefine pi to be 3.2 because that would be more convenient to the building industry. It was vetoed by the governor, but to me the most mysterious aspect of this precursor to the Tea Party was, if you're going to redefine pi, why the hell not make it 3 instead of 3.2? But nonetheless, I digress. One of the things that characterises most of beauty in mathematics is that, by and large, if you make the assumptions, you prove the theorems. Some of the theorems are still too hard to prove, and there's a prize of $1 million for Hilbert's 7 unsolved problems, one of which has been solved by a very eccentric Russian who has refused to take the $1 million because he didn't really feel that it would enhance his life, and several other mathematicians who felt they were vaguely helpful have written generously offering to take the prize in his place. And then there are things where we've proved the theorem, but the proof is so ugly that some people feel it's not very useful. I mean, the very simple proposition that any map you can imagine, any two-dimensional map you can imagine, you can colour all the territories using only 4 colours, and you'll never have a problem of confusing things at the boundary. And that was finally proved by a lengthy computer calculation that examined oodles of cases of exceptions and showed they were all exceptions. And so it showed that the thing that everybody already effectively knew was right really was right, but it was so ugly, that no enlightenment, that some people would say, yes, it's a proof, but it's not mathematics. More startling is something that emerged only about less than half a century ago, which really undercuts the basic thought that if you've got the mathematical equation, you can predict the future. This is the Newtonian dream, that if there are laws of physics that govern the motion of the heavenly bodies, then we can always predict what's going to happen. And here is an interesting equation that some of you will be familiar with that is a counterexample. And suppose X is the number of knapweed gallflies in Whiteham Woods 1 year, and X next year, the next X, xt plus 1, is some multiple of the number this year as they reproduce themselves, so some number A that will usually be bigger than 1. If it's less than 1, the population's going to die out. But it's not just A times X, because if the population comes too big, it begins to interfere with its environment, eat itself out of house and home, so you put in a negative feedback term. And that's a little simple equation that's been put as descriptions of fisheries, of certain kinds of insect populations, and you can draw it as a graph. The next X is this sort of parabolic, curvy thing, increasing at low density, decreasing at high density, and the potential equilibrium value of X is when the next X continues to equal X, and you can see it along that dashed line. And that all sounds perfectly straightforward, but if you actually start running that equation out, you discover as long as the constant A, if it's less than 1, the whole thing just dies out. If it's between 1 and 3, the population settles to some nice steady value if there's no random elements in it. But if the number gets bigger than 3, it becomes unstable and starts oscillating up and down, driven by its own internal dynamics, but still predictably. If the number A gets beyond about 3.5, it starts behaving in ways which superficially look indistinguishable from random noise. It just wanders around like that top curve. In fact, if you ask what are the fixed points of that equation, what are the values of X in that equation, such that for that value of X, the next X is the same. These may be stable fixed points that the thing will converge on, or unstable fixed points, like being balanced on the top of a billiard cue. Yes, it's a point which will be the same next time as long as nobody looks sideways at it, but the tiniest perturbation it will move. And so you plot the fixed points of that quadratic map. At first there's just one, then that goes through a cascade of period doublings, and then it wanders into an ill-understood area that several people independently discovered as a mathematical phenomenon in the 50s. 3 or 4 people, none of them saw it as other than an arcane mathematical property, but I had independently discovered the period doublings, and more importantly, Jim York at Maryland, who gave us the word chaos, had discovered that if one of these sorts of difference equations, next X is some function of X, has a 3-point cycle, then for the same equation with all the same parameters, you could find other cycles of every integer period. And that's in the chaotic region. Once you've got period 3, which is that bit of a window, you can, with appropriate starting conditions, find every other integer period, and many of them, 93 different 11-point cycles. And he very properly called it period 3 implies chaos. But it's not just a mathematical curiosity. This is a really interesting thing. Not only does that look random when you run it out, but in the chaotic region, systems are so sensitive to initial conditions that even though you know the equation, and the equation's simple, you can't predict long term. And I show you an example. There's that thing we were just looking at with the constant A is 3.8. You started off with the initial X as 0.3, and you get those firm lines, rather random looking, but generated by the equation. Suppose you make a mistake of 1 point in 1,000, 1 part in 1,000. Then instead of 0.3, it's 0.301. First few iterates are similar, Then it begins to diverge, and 10 iterates out, it's about as different as it can be. Interestingly, you can predict just short term, and one of my ex-graduate students, we wrote a paper in 1990, it opens a new window on short-term predictions of certain kinds of nonlinear algorithms. In fact, the random number generator that von Neumann and Ulam used in the first computer that was built in 1948 at the Institute for Advanced Study used the quadratic map as their random number generator in the chaotic regime with A = 4. If you test it by conventional tests of random numbers, it says they're random numbers. But if you devise a test that applies to say, this random-looking stuff maybe got elements that are a non-linear equation behaving chaotically, using the method that George Sugihara and I developed in 1990, you can make short-term predictions within a certain short-term window, and George parlayed that with the rise in algorithmic trading into running Deutsche Bank Securities USA for 4 or 5 years. And that's how I eventually got drawn into banking things that I'll talk about right at the end. George made an 8-digit fortune in 4 years, and then being the kind of person he is, he decided, been there, done that, more money than he needed in this and several other lives, back to university to work on something more interesting. Less remunerative, but more interesting. Suppose we take the quadratic map and put it together with the complex number bit. Instead of having the next x is ax 1 minus x, we'll have the next z is z, az 1 minus z, where z is now a complex number and a can be a complex number. We've now got sort of two-dimensional version. If given that z is itself x plus iy, if we write the real part of that complex number equation in z and the imaginary part, we'll get two equations and we'll get a two-dimensional analogue of the thing I've just been talking about. It's normally written in a different way for people who are familiar with the Julia set. And what you can generate now from that two-dimensional array of things, you can look at what are, for a given value of the constant a, which could be a complex constant, you can ask, what are the fixed points of this? What are the things where the next z will be the same as z? These were things that had been looked at without appreciating the implications by a French mathematician called Julia early in the 1900s, and it was Benoit Mandelbrot who brought them centre stage, and the Mandelbrot set is one particular example of a Julia set, but with one particular value of the complex constant a. And it's an interesting comment on the sociology of science. Most mathematicians really disliked Benoit Mandelbrot, because he was an egotistical sort of bloke, but a really interesting bloke. And they said, but Julia had done all this. Julia said. Julia had seen it as a mathematical curiosity and had no sense of how interesting. Mandelbrot saw it as really practically interesting and important. And the same is rather true of the simpler quadratic map that I was talking about, Jim York. Jim York is fond of saying, other people had seen this mathematically earlier. We weren't the first people to see this, but we were the last, because we saw it was interesting. So that's one thing to find it, another thing to see it. But the things you do generate, and many of you will be familiar with this, are really not just aesthetic. This is the real highlight of the beauty and mathematics bit. This is the Mandelbrot set, and it's this two-dimensional thing, the quadratic equation with a complex variable, and these are its fixed points, and they define an object which has a finite area. You can inscribe a circle around it, and all the fixed points are included within it. It's got finite area, But if you try going round the boundary's got twiddles on it, and the twiddles have got twiddles on them, and the twiddles of the twiddles have got twiddles on them, and the boundary is infinite. And that's a curious concept. There's more detail than you can show, and this is just to give an idea that the details stretch out in more increasingly filamentary forms into these outer colour areas. And if you blow them up, you get bits like this. This is one of the twiddles blown up. And you can take one of the twiddles on one of the twiddles and blow them up. And you get all sorts of stuff like this procession of elephants. It's marvellously complicated. And that, to my mind, is the apotheosis of beauty in mathematics. And it has its amusing elements. This is a particularly elaborate crop circle that some bunch of pranksters put in place one night. They must have worked very hard, and it wasn't just one of them. And there are people who are not at all put off by this fiction that it was done by pranksters. This is clear evidence for extraterrestrial visits. I'm now going to move on to the second bit at an accelerating rate. I've only been going 20 minutes. To what extent, however, is this principle of elegance useful as a guiding principle in trying to explain real phenomena in the real world as distinct from just understanding how the potential properties of a dynamical system? And this goes back to Galileo, in a way heartwarming to any mathematician, who said, roughly translated, that the grand book of science is written in mathematics: circles, triangles, squares, other geometric objects. And it's been restated by other people. Jean Vignes speaking of the unreasonable effectiveness in mathematics in explaining the world. Or somebody whom I have forgotten, suggesting that if indeed there is a God, he clearly, or she, is a mathematician. And that, I think, is an abiding truth, although these days we'd recognise that the book may be written in mathematical terms, but its objects can be much more complicated than circles and triangles and simple Euclidean objects. They can be all sorts of fancy attractors and chaotic behaviour. So we come back to the abiding question of to what extent is it, can we be guided? Is beauty truth and truth beauty? Is that really all you need to know? And I'd say sometimes, but sometimes not. And I'm going to give two examples of really, two examples of really extraordinarily important advances which were based ultimately on empirical observation, but which were guided by aesthetic principles. The first one is Einstein, and I'm not going to talk about general relativity, but I'm going to outline special relativity. And the second one, most appropriate, and it's partly why I chose to talk about these things, is Dirac. As you know, in the middle 1800s, James Clerk Maxwell brought together what people thought were two different forms, two different phenomena, electricity and magnetism, and unified them in a very elegant set of equations. And that led to the concept of a pervasive fields that, which were the terms in which the equations were expressed, and then the corresponding notion of some ether in which they were embedded. And it provoked people to start asking, given that the Earth is moving, what's its motion relative to the ether? And the Michelson-Morley experiment, very exquisitely delicate experiment done at the California Institute of Technology in the late 1800s, couldn't detect any movement relative to the ether. So that means either somehow the Earth, it's a wonder to me, and I can find no trace of it, that it wasn't seized upon by the religious community, particularly religious fundamentalists, as evidence that we are unique in the universe, that we are unique in all creation, because the Earth has the ether attached to it, and everything else moves relative to it. And I can find no evidence that anybody was interested enough in the science to catch on to this fallacious argument. But on the other hand, it's about as plausible, when you first think about it, as the alternative that solved the problem due to Einstein. I mean, the imaginative leap of saying the answer to this is that the velocity of light simply must be an absolute constant. Doesn't matter whether you're running towards it or running away from it, the thing you're looking at, the velocity of light is an absolute constant. And if that's true, and the laws of physics are the same at all times, in all places, if they're true, then notions of space, how big is this lectern, and time, how much longer am I going to talk, are relative. And there are going to be corrections, and that's a hugely counterintuitive thing. In pursuing that notion, Einstein said, well, let's just consider this four-dimensional system of the 3 dimensions of space and the dimension of time. These 4 dimensions are in a universe where the speed of light is an absolute constant. The immediate implication is that there are going to be corrections to our classical Newtonian notions of momentum, velocity, and you've got to correct a measurement of a particle's momentum by terms which are of the order of velocity over velocity of light squared, which is usually extraordinarily tiny. And I am not going to make any attempt to inflict upon you the derivation of that. Einstein then went on to say, what is the corresponding implication in this unified treating time and space symmetrically? What is the analogue then, what does it imply for the measurement of energy that we associate with movement and momentum, now that we've unified time with it? And what came out of the mathematics, guided purely by these principles of, as it were, elegance and the unification of space and time as relative things rather than absolutes, was the notion, which really weird notion at its time, that any object, again, like this desk, even if when it's completely stationary, is in possession of a rest energy which is proportional to its mass times the square on the speed of light. And that if you could somehow make some of the mass disappear, you would release the energy, because energy is conserved. And at the time, that seemed A, implausible, and B, completely abstract. And yet that is the foundation, obviously, as we all now recognise, nuclear fusion, nuclear fission, you lose mass, you create energy. That abstraction, guided by pure principles of elegance and consistency, has transformed our world, and it's transformed our world into a world in which, as Steve Weinberg has eloquently written, borrowing a phrase from Yeats, and it was an essay in the New York Review of Books that I gave to Blair, but seemingly to little use, called Slouching Towards Apocalypse. And we live at a time when this is again the consequences of that piece of beauty and mathematics in pursuit of understanding is the consequences really are appreciated. And you can see, if you actually look at it, the expression, the momentum becomes mass times velocity with that correction, square root of 1 minus v squared over c squared. So I leave it to you to either read that out or take no notice of it. But you'll find if you write down that expression for the energy that comes out of the symmetrical treatment of space and time, then you get the rest energy, mc squared, and then you get the conventional classical Newtonian kinetic energy, a half mv squared, and you get correction terms that are relatively of order the velocity over the velocity of light squared, which is almost always negligible. So I conclude with some words about Dirac. And Dirac came after Einstein. Here we now have a world in which Schrödinger and other people have explained some other phenomenon that I haven't talked about by explaining that we don't ever really know exactly where a particle is and at the same time how fast it's moving. All we can do, the best we can do is get an equation for some probability, some probabilistic description of the system, which is pretty weird and which Einstein really did reject right to the end of his life, feeling that. And there are still those who feel maybe this is some extremely arcane expression of chaotic dynamics, where there is a determinism, it just looks probabilistic. So Schrödinger had given us an equation that described the mechanics, quantum mechanics seen in spectroscopic phenomena and others. And Einstein had told us that the classical framework that the Schrödinger equation was extending to take account of quantum dynamics itself needed to be reformulated relativistically. So Dirac set himself the task of reconciling special relativity with quantum mechanics and getting the relativistic version of the Schrödinger equation. And it can be written various ways, but I have chosen the way that is in the memorial slab to Dirac in Westminster Abbey, which is this way that has got rid of a lot of the parameters, the constants, by rescaling things to make it tidier. So here we are, here is the equation that reconciles relativity with Schrödinger's equation. Begins with I, square root of -1, our old imaginary friend. The next thing is gamma, and I'll come back to that. And then these are really 4 equations, and gamma is a matrix, 4 by 4 matrix, which I'll come back to in a minute. And then the delta symbol means the derivative with respect to the 3 dimensions of space and time of this thing psi, which is the wave function, which gives you the probabilistic description of what the particle or other object is doing, and that's equal to the mass of the particle times psi. And the guts of this is in that 4-dimensional thingamy, that 4 by 4 matrix gamma, which corresponds to 4 basic particles, 2 of which are identifiable. They're electrons, fundamental particles with negative charge, with spin up or spin down. So 2 of them are electrons. And the other 2 are sort of anti-electrons, with spin up and spin down. So this is all sounding now a bit weird, but very elegant, very symmetrical framework, it's logical extension. But what are these anti-electrons? For a little while, for a brief while, Dirac thought maybe they're protons. That would be neat, and then we've got electrons and protons and the thing. But that clearly didn't work because protons have mass something like 1,800 times that of an electron. And then he made what I think is the boldest and most astonishing intuitive leap that has ever been made in science. He said we can reconcile all of this if throughout the entire universe all the possible quantum states of anti-electrons are full. And the only time we'll see their expression is if there's an occasional vacant space, which will then behave like a positive electron. So electrons we're long familiar with. They're sort of all around us, familiar objects. And Dirac said they have an opposite, sort of positrons. Positrons are the tiny handful of missing anti-electrons which pervade the universe and are completely undetectable. And it sounds like you publish the paper, you're going to be institutionalized. Dirac got the Nobel Prize, which he shared with Schrödinger. And I think I'm right, he got it sooner than Einstein, certainly around the same time. The reason is simply that the Nobel Prize wants to see experimental verification for the idea, particularly an idea as crackpot as that. And Einstein had to wait till some of the bending of light things were done and so on. But maybe he didn't have to wait, but it was a long delay. Whereas Dirac, this was all done around 1930. It immediately, this equation, just this equation, the way it's written, it immediately explains the puzzling fine structure of spectral lines of elements, and solved the problem of how do you explain the magnetic moment of the electron. And it gave those to sort of multi-digit accuracy, so that was a triumph. But then in 1932, positrons were found. And so he got the Nobel Prize the next year. A truly astonishing thing, greatest achievement, life of the mind, I think. And it raises it, now I'm going very briefly into the final part of the lecture as I waffle about this and that. And two things, really. It's a very interesting question. Why is it that Einstein is such an iconic figure? You see him all over the place with his tongue hanging out, as it were, these days in that rather tasteless poster. And most people wouldn't identify with Dirac at all. And the reason is basically simple. Einstein actually courted publicity, and Dirac shunned publicity. Einstein's an interesting figure. He's one of the few celebrity figures of science, and he's a celebrity figure essentially for the wrong reason. Celebrities are people who are famous for being famous. And that's exactly what Einstein's status as an icon is. He's famous for being famous, but you ask all the people who've heard of Einstein, what did he do? And they'll tell you the words, relativity, but they don't have a clue what it means. In that sense, he's exactly like Dirac. He did something profoundly imaginative, counterintuitive, guided by principles of excellence, of elegance, and it turned out to be right, and it changed the world. But they're different in the kinds of people they were. And I want to, it's not my last words, but close to it, those who would like to learn more of Dirac, there has recently been published a most admirable book, and I have no financial interest in it whatsoever, by Graham Farmelow at the Science Museum in London, called The Strangest Man, which is a biography of Dirac, and it's a great read. When I gave this lecture in Cambridge, the last bit, I went on to a more waffle about the nature of science and policy, but here I'm going to close with a remark, seeing as somebody did mention that my current interests are I'm engaged with people at the Bank of England and others in trying to understand a little bit better what actually did go on, what went wrong, and I'm not going to inflict all that on you, but relevant to the question of just what is the nature of the way we judge whether things are valuable or not valuable. The sciences, the natural sciences, the life sciences, the physical sciences have advanced through experiment, and I've not really answered the question, did the advent of the experimental method, where you don't sit around arguing whether heavier balls fall faster than small balls, you don't sit around thinking that wise philosophers, by appeal to the authorities of the past, can answer the questions, you bloody well do experiments. Has that sort of taken some of the beauty out of things? Well, maybe it has, but what it has given us a really powerful weapon. And one of the things that I found interesting, and I'd never really thought about it, as I started to learn a little bit more about both the economic foundations of what were the way that financial instruments were being created, and the way that people judge this and the way people are discussing in politics what to do next. It's much more like Socrates' Athens than it is like science. It's appeals to authority, and it's hard, admittedly, to have much data in economics, but you know, if you're a right-winger, you don't like Keynes, and if you're a left-winger, you do like Keynes. And it's just bizarre to see these things being discussed in this way. And if you look at the way some of the instruments that caused the initial catastrophe, the credit default swaps, it's not as if people, sensible, down-to-earth people who are not mathematicians or any sort of scientists like Warren Buffett, in his essay to the shareholders in Hathaway Barclay in 2002, written in plain language, Google it and read it. It's a great read. His letter to shareholders that acquired an insurance company that had a lot of credit default swaps. He took one look at them and he said, these things are crazy. They're financial weapons of mass destruction, he said. I got rid of them all. And many of these things, what people did, they took bunches of triple-B mortgages, they put them together, effectively using, and it was cloaked in appeals to economic language about efficient markets and stuff, which are sort of fictional concepts, but it amounted to saying, we can treat all the mortgages as uncorrelated. So you put together a bunch of uncorrelated triple-B mortgages and the central limit theorem works for you and it's less risky. Mortgages are uncorrelated? There are lots of interesting books about this, and one of my favourites is a book called The Big Short, written by one of several colourful characters who saw how silly it was and made a lot of money out of it. And at the end they're talking, and one of them says, were these people really stupid, or were they crooks? And there's one darker character called Vinny, and Vinny says, most of them were morons, but some of them were crooks, and the higher up ones tended to be crooks. Well, in the op-ed accompanying the Nature article I wrote with Andrew Haldane, who's the Director of Systemic Risk at the Bank of England, we wrote an op-ed thing for the Financial Times, and I think we summed it up in a way that's not strictly fitting this lecture, but touches on these points. It says, the present situation in banking is in many respects perverse. The magic of diversification, when assumed into banks' risk models, means that large, complex banks often hold less capital than their smaller, simpler brethren. The rocket scientists building models tell us this makes sense. But the rocket scientists building rockets tell us it's nonsense. When you try and talk to the bankers and explain that this is nonsense, the reaction is anger and leave us alone, and the discipline of markets will restore everybody's financial health, and if you don't do it, we'll go to the Cayman Islands. And in Britain at the moment, alighting from this, there's a more sort of scientific inquiry going, led by a very, very good person, John Vickers, an independent banking commission, whose interim report touches on some of the things that would make the system more secure, and it's much informed by some of these, looking at it as a dynamical system, and asking at least what such dynamical systems would do, that it would make more sense for the bigger banks to hold relatively bigger capital reserves. Never mind that of course they're bigger, but so are their liabilities bigger. You want them relatively bigger, and that might just get through. But the more fundamental reform, which I would do if I were supreme dictator, of saying, let us not have people trade in instruments that are so complicated that you can't price them properly, and insofar as you have to have them rated, let them be rated by public agencies, staffed by people whom, if necessary, you have to pay them a lot, are really good, rather than having them evaluated by private agencies who go out of business if they're too diligent. So now, not only were these things putting triple Bs together and saying they're all uncorrelated, but the rating agencies were saying, yep, AAA. Very weird. So that was a gratuitous add-on at the end, but seeing as people mentioned it briefly in the beginning, and it does resonate in some broad, basic sense with the themes I've been making, that elegance is still an important tool in understanding things, and so I have a sympathetic view of string theory, which many would think is, as they might have thought of Dirac's idea of positrons if you hadn't found them. I have a sympathy for it, but I feel it's an example of something that's guided probably too much by elegance and is too little in trying to be in touch with reality. And I think the mixture of trying to understand things in simple ways that you make more complicated, guided by the principle that maybe, as it were, God is a mathematician, is a useful tool, but a tool always to be distrusted, and seeking ways to test it against reality and recognising that the ugly fact always has to trump even the most elegant theory or even the most respected of the canonical entities that you pay obeisance to, whether they be Keynes or Milton Friedman.
I'm delighted to say that Lord Mayor's happy to take some questions. We do have some roving microphones, one I can see over here and one down the back. So if you could identify yourself and find a microphone.
Viv Robinson. What Dirac, when he did his equations, he pointed out that was, it works, but he doesn't really know why. I'd just like to pass a comment. There's a paper going to come out in the next week or two, which gives a reasonably good description of why the electron behaves the way it is. I'd like to discuss it with you later on if you like. And the other thing I'd say in relation to a comment about Einstein and Dirac's fame, E equals mc squared is a lot easier for the public to say than I gamma d phi equals m phi, which most people don't understand. Thank you.
One of the problems we have is in science, of course, as you pointed out, is that we can't prove anything the way, with absolute certainty, the way mathematicians or religious zealots can. And I was wondering if, in your experiences in communicating with politicians and so on, and having thought a lot about elegance, which is something that we use to try to deal with this, whether you have any advice for those of us who are trying to communicate scientific findings that people don't want to hear, and who are able to use our inability to prove something absolutely as an excuse not to take it on board.
And I say it depends on two things. First of all, it depends on the kind of, who are the politicians? There are personal things in these, and it also depends on how you go about doing it. Britain, I think, has been rather lucky, at least for a period through the 90s and relatively recently, in having, when Kinnock lost the election, one of the Labor Party manifestos was to create an independent Office of Science and Technology, which had a permanent secretary as its head, but the permanent secretary was someone brought in from the outside world. And that was a change from what many countries have and what Australia had until she resigned just the other day, which is a sort of ad personam appointment with a staff of one or two, sometimes a part-time thing, but rather to create something that was part of the machinery, part of the Sir Humphreys who get together on Wednesday morning and so on, and someone who reported directly to the Prime Minister. And that has been, I think, a quite powerful voice. It's relatively new. I was the first person who came in under that system, and succeeded by Dave King, and now succeeded by a close friend, John Beddington. And in many respects, that has not worked as well as it might. And in other respects, it's worked really rather well, and the success of some of the partial successes of each of us in turn have been consolidated and built on by the next person, so that by this time every department has an outside person brought in with a small staff as scientific advisor, and these are good people, and they all get together themselves as a sort of mini permanent secretaries meeting to share their problems. John Beddington has managed to get the following, which is a really extraordinarily good outcome. No government department may cut its spending on research and development without his involvement. So each individual thing, department by department, and we've got a regime of pretty rigorous cuts at the moment, but Cameron is going to be obliged to at least hear the contrary case, bit by bit. That's the sort of machinery you need, but there's no recipe for achieving the machinery. And even if you've achieved the machinery, it's going to depend on the people you get to do it, and it's going to depend on the people who are listening. And you need to create a climate in which it becomes politically difficult not to at least show that you're listening. And that requires an engagement and an outreach to the public so that they also have confidence in the process. And all of that's a lot easier said than done. And so I pointed to some of the successes. It simply has been unsuccessful in respect to GM foods, where the opposition, an extremely skilled corporate activity by Greenpeace PLC and other entities which now are in effect corporate bodies with estimable aims, but sometimes rather scientifically confused. But once they've got an aim, and as I say, their motives are good and they do more harm than good, more good than harm, I think. But nonetheless, once they've decided on a policy, they pursue it like a corporation. So they first of all alert that Brent Spar shouldn't have been disposed where it was planned to be, and they were right. They prompted a better survey that said what should be done with it, but what should have been done with it is disposed at sea in a different way. But their corporate aim was to have it not disposed at sea, and that had to be satisfied, and that overrode all the science, and the net result is disposal was more damaging than the original that they'd complained about. So you've got these complicated things, and yet when you tell a well-intentioned NGO that it has a conflict of interest because it functions like a corporation, they get very upset. And that was a long answer to a very good question. And the short version of the answer is there's no recipe. It depends on taking advantage of chance, and it depends on the temper of the times. And however well you do, you'll have successes and failures. Australia, it works. Accidents can help. Ralph Slatcher was hugely influential here. He went to school with Bob Hawke. And I think there hasn't been a person since who's had the advantage of a really established office along the lines of the British one, or the Swiss one.
Peter Swan, Australian School of Business. I was very interested in your remarks at the end of your lecture about global financial crisis and size of assets, size of banks, because one of the strongest results that I and a colleague have got when we look at the probability of a bank either being failed or being bailed out during the crisis is size. The larger the size, the greater the probability of failure. And I always thought this was due to being too big to fail, that they knew the government would bail them out, and the bigger they were, the more likely they were to be bailed out, and therefore the more risks that they take. But now you're suggesting, I think, that perhaps there's something intrinsic between size and probability of failure. Perhaps you could elaborate.
I think one of the factors at the heart of the banking problem is there is a real tension between what's in the interest of individual banks and what's in the interest of the system. So Basel I and Basel II put an emphasis on individual banks diversifying, and that's very sensible. So suppose you had a bunch of, for simplistic way, suppose you had 10 banks and 10 different sorts of things they could be doing. And each of these sorts of things that they could be doing, each of the 10 different kinds of assets, has some probability P of 10%, 1% of failing at a given time interval. If each of the banks held all of one of the asset classes, so they were all different, the chance of any one bank failing in the given time interval would be 1%, and the chance of them all failing would be 10 to the minus 20. So you wouldn't. On the other hand, if each of the banks held a tenth of each of the assets, the chance of an individual bank failing would be much less. But seeing as the banks are all now identical, if one bank fails, they all fail. And that expresses one of the elements, only one, but one of the elements that has occurred as a result of what things have happened, but by no means the only one, in that Basel I, Basel II have prompted diversification of individual banks, which has tended to make them all somewhat more similar, so that although it was indeed and continues to be in the interest of the bank looked at one by one by one, it's not in the interest of the system. There's a tension between the interest of the individual, tension and the interest of the system. And there's a lot of other factors in it too, of course. But I think that is an important one, and there are various ways you could try and get around it. Some of them, I think, a little bit too abstractly elegant, of like trying to work out what's the cost to the system of different kinds of risk instead of asking about the cost to individual banks, and trying to put some regulation on the tensions between diversification of individual banks and diversity of the system. But it's easier said than done, and particularly maybe the economists involved in it would be and are sympathetic, but the people who run banks are by and large not. And that also is understandable, because they have a system whereby if things are going well, they get obscenely rich, and if things are going badly, we pay for it. And that's a great thing, tricky. I mean, some of these, there are some formal analogues between the romantic notions in ecology 50 years ago of the balance of nature, and the notion that complex systems, by virtue of their complexity, were more robust. Whereas in fact, when you look at things, you discover that by and large, increasing complexity is increasing fragility, and turns the question on its head and asks, what are the atypical structures that characterise particular ecosystems that reconcile complexity with robustness? And those things don't easily read across into banking. And Andy Haldane has a wonderful phrase that sums it up. He said, ecosystems are survival of the fittest. In banking, with increasing trends, what we're seeing, with too big to fail, is survival of the fattest. And it's not easy to address that.
Regarding Albert Einstein, now as far as I know, correct me if I'm wrong here, his solution to the ether problem was originally deemed by the scientific community as actually inelegant. So I think there were one or two physicists before, quite well-known established physicists, who actually produced a theory in line with the ether argument that was quite elegant, and it was quite well held on to by the scientific community, and Einstein was more attacked because of him dispensing with the whole idea of the ether, so it was considered less elegant. So I guess the point I'm trying to make is we can't always use aesthetics as a guiding principle in our scientific and mathematical theories. But now that you mentioned string theory, what I wanted to say is that that's now a very well established field in physics, theoretical physics, and maybe that's one of the big problems that we have today, is that we're making the same mistake that people made in Einstein's time. And so now just the question I'm trying to ask, that I want to ask, is that do we have a community right now in physics that actually enables people like Dirac or Einstein to actually flourish? Or do we just have these massive, I suppose, financed institutions that only go with the main status quo and not with sort of more fringe ideas? That's the question. Thank you.
It's a good question, but in the light of the time and my inability to give a good answer to it, I think we could appropriately end as Dirac was in the habit of responding to questions. He either said yes or he would say no. Or sometimes he would just be silent, as you know. There's a celebrated thing, a person who said, I didn't understand, and he got from that line to that line. There was a long silence. And the chairman said, Professor Dirac, you're going to answer the question. He said, that wasn't a question, it was a statement. So I'm afraid I'm going to cheat and just say yes and no.
We'll wrap up the formalities. I'll ask Professor Richard Newberry, who's the head of the School of Physics, to formally thank Robert Lord May.
Lord May, thank you so much for spending the time to visit us today and to give a wonderful lecture, which was informative and enlightening and also entertaining. I'd like to thank local people who've supported and sponsored your visit. In particular, I'd like to thank the Australian Institute of Physics, the Royal Society of New South Wales, and the Faculty of Science at the University of New South Wales. And the individuals that have particularly supported this are the Dean of the Faculty of Science here, Merlin Crossley, who couldn't be here today, Professor Richard Henry, who's spoken, our Deputy Vice-Chancellor, Fred Osman from the Institute of Physics, John Hardy from the Royal Society of New South Wales, Heinz Horer, who's contributed a lot of work in organising today's event, and last but not least, Xanthi Chapman from the UNSW Foundation, who's done a lot of the running around and has ensured that today's lecture has run like clockwork. So thank you very much to all those people, and thanks once again to you, Lord May, and a safe journey to Canberra this afternoon.